Alright, so this is my first video in this physics course that I'm providing. And in the first video, it's important to talk about sort of the basic mechanics, right? So the basics of mechanics. And in mechanics, we talk about two particular things called kinematics and dynamics. These are sort of at the foundation of any discussion of mechanics. So kinematics and dynamics. Now, these are words that are used interchangeably a lot. That people use them interchangeably a lot, but they're really not interchangeable words because these have different meanings, right? Kinematics is basically, in a simple couple of words, is a mathematical description of the present state of an object. So it's a math description of present state. And by that I mean the present state of motion of an object. So it's basically a way to describe in math how an object is moving at the present moment, right? And dynamics is it's sort of a description of how and why this particular state of motion changes with time. So how and why, motion state changes with time. So basically this is describing what are the conditions at the present moment. This is telling you how those conditions change with time. So these sort of two things come together to give us a description, a complete description of objects that are moving in our discussion of classical mechanics. Objects that are either moving or at rest or in any particular state. But this is basically how we describe them in the sense of classical mechanics. Right? So in classical mechanics, one of the first things we talk about is an object's average velocity as well as its average acceleration. So when we look at an object, right? A lot of times we look at its motion in a displacement versus time graph. Now this x of t represents the motion of the object in the x direction, and t represents time. So this is basically, you're already seeing how this definition comes into play. This is a present description of one of the aspects of its motion, where it is currently. And the dynamics aspect comes in when we explain how those things change with time, right? So let's just say that this object is moving in some sort of trajectory, some random, trajectory, right? This is how it's moving throughout time, right? And we want to find the average velocity between two particular points in this trajectory. So we might choose this point and this point. Right. So this point is at a time t1, and this point occurs at time t2. And at those times, the object itself is at a position x of t at time 1, right? Because this is a function of time. The position in this trajectory of the object that's moving, the position at every particular point is a function of the time of the time value that we're looking at in that trajectory. So this is x of t1, and this is x of t2. X at time 2 and x at time 1, right? So if we're looking at this trajectory and we want to find the average velocity of this particle when it's moving from here to here, right? This is it's an average. It's basically, it doesn't tell you anything about a particular point. You're just looking at it as sort of the average velocity during this whole entire trip, right? When we look at average velocity, and we often designate it with this sort of velocity with a bar over it. That bar usually kind of means that we're talking about an average. Right? It equals x at t2 minus x at t1. Right? This is the change in the position over t2 minus t1. This is the average this is the average rate at which position is changing throughout time between these two particular points. We could do this with any two particular points. We could take this point and this point, and this point and this point. And as long as we know what the endpoints are, and we know what time values they're occurring at, we can find the average velocity. Now, with average velocity, following that, there's also something called the average acceleration, right? So the average acceleration requires something more than just the positions at these points, but it requires the velocity at those particular points, right? So you would have to sort of translate this graph into some sort of velocity versus time graph, right? And you would want to know the velocity at t1 and the velocity at t2. And I'll discuss in a minute how we find velocity at particular points and not just the average. But I want to have a discussion about average velocity and average acceleration. The average acceleration, which is acceleration a with a line over it, is equal to v at time 2 minus v at time 1 divided by t2 minus t1. Right? This describes the average velocity between these 2 points, and this describes the average acceleration between these 2 points. In order to find the average acceleration, we would have to find the velocity at those points. And the velocity at those points, as well as the position at these points, are what are called instantaneous values. They are different than average values because average values look at values over a large range, but an instantaneous value tells you the value of something right at a very specific point, not a large range at all. So to sort of discuss instantaneous velocity, I'll make some space over here to continue talking about instantaneous velocity. When we talk about instantaneous velocity, what we are talking about is, if you can imagine, again, that we have that graph that we had before. Maybe something similar. I don't remember exactly how I drew my trajectory, but let's just say it's this sort of trajectory. Right, and we choose 2 points. We could choose any 2 points. We could choose this point, and we can choose this point. This is, of course, still our x of t versus t graph. And this is x of t1, and that's x of t2. And these are time 1 and time 2. The instantaneous velocity at a certain point, you can imagine, is not an average over a large distance. If we wanted to find the instantaneous velocity at this point, you can imagine that this range would have to be much smaller. It would almost have to be at this time, and then another time that is there's virtually zero difference between this time and that other time. It's kind of the same description of our average velocity, but the range in time would have to be so small because we want to get it to this point. We want to find the instantaneous velocity at this point. So we have a very different description. So if I wanted to find it at t1, let's say, right, and I want to find the instantaneous velocity, I'll write inst for short. I don't like how I drew that, but it's okay. V, which we call V without any sort of line over it, is going to be the limit. It's going to be a limit as delta t approaches 0, because we want delta t to be basically 0, right? We want it to not be this large delta t, but we want it to be pretty much right where it started. And we have this of delta x, delta t. For t, the delta t being very small, right? Because we just basically want it at that exact point. The nature of finding velocity is sort of finding, you're basically finding a difference between 2 points in position and in time, which is shown here with the delta x and the delta t. But if we want it at this particular point, that other location in distance and time has to virtually be right there. So that's where this description of delta t approaching 0 comes from. And this very description is what's called the derivative of x as a function of t with respect to time. So velocity, instantaneous velocity, is equal to the function of position with respect to time at a particular point with respect to time. So you could imagine that if we had some graph that wasn't so like random and we could actually draw a function for it, right? Let's say we had x of t is equal to t squared, make it very simple, right? The velocity at any point, which I should actually write as a function of t, because it's also a function of t, would be dx dt. Now, if you have any elementary experience in calculus, you'll know right away that that's 2t. So this is the function of velocity with respect to time. And then at any particular time, you could find the velocity. If you wanted to find it at t is equal to 1 second, it would be 2 meters per second. If you wanted to find it at 3, you could plug in 3 here and you get 6, right? Meters per second, or whatever units per second, because it might not be meters in this case, but usually in the traditional physics sort of usage of SI units, we use meters per second. So instantaneous velocity is the derivative of the position function with respect to the position function of time with respect to time. And there's a very simple example here that shows how that works. So once again, now we can know the velocity at this point and this point, because all we'd have to do is have the position function, take the derivative of it, take the derivative, and what we would do with the derivative is we would plug in the different t values at this point and at this point. And then that's how you'd find the velocity at this point and then the velocity at that point. And then you could find average acceleration, right? Because all that average acceleration does is it takes the velocity at this point and at this point, and it subtracts them and divides it by the difference in time from this point to this point. So with that, we also have what's called instantaneous acceleration. Instantaneous acceleration. And instantaneous acceleration is a step up from here. It would be, well, it's the limit as delta t approaches 0 of delta v over delta t. Right? Remember how our other definition of average acceleration was that it was the difference of the instantaneous velocities divided by time, the change in time. But once again, with instantaneous acceleration, we want to know acceleration at a particular point. So we don't want to know it over this large range, but we want to have it at such a small range that it's essentially at the same point that we started at. So this delta t is going to have to approach 0. And this is what's called the derivative of velocity with respect to time. And this is also the second derivative of position with respect to time. That's the second derivative of position with respect to time. And in most of the cases that we talk about, basically the remainder of this course, the instantaneous acceleration will be constant. It'll be just, acceleration will be constant. That'll be called, that's what we call uniformly accelerated motion. So we could kind of use this situation here where if now you have this instantaneous velocity, you want to find the instantaneous acceleration, right? All you'd have to do is do dv dt and find from here that it would be 2. Some constant. It doesn't change with time. This 2 will never change because it has no t in it. Make it change. And that is a basic description of how acceleration and velocity works. And in the following videos, I will sort of make I'll have a more in-depth look at velocity and acceleration, which will lead to the kinematics formulas that I was talking about, the mathematical description of an object at its present state.